Now, the electric dipole is interesting because its net charge is 0, but yet it has an electric field associated with it. With a dipole, we can define some vector d, which represents the effective dipole of the two charges. We call this the dipole moment, where it becomes stronger as the positive charge and negative charge separate, and as the individual charges of each becomes greater and greater. Now, if I move the charges close to one another until they overlap, effectively they will cancel each other out, and therefore the net electric field will be 0. As the separation becomes greater and greater, the field begins to become more and more pronounced. And therefore, we can represent this dipole strength, this electric dipole. Sometimes it's represented as P, sometimes it's represented as mu, as again, the charge of each charge. So positive charge would be positive Q, the negative charge would be negative Q, again, times the distance that they are separated. And the vector itself, this is a vector, points in the direction from the negative charge to the positive charge. Again, this is generally the opposite direction that the field lines are pointing at. Now, the SI units for electric dipole moment are coulombs meters, because we're taking the charge times the distance. And we can convert coulombs meters into another unit called a debye, named after the person who studied dipoles. And 1 debye is actually equal to 3.34 times 10 to the minus 30 coulomb meters. So when looking at atoms and molecules, the dipole moments for them are extremely, extremely small. And typically, if we want to take a look at a very polarized molecule, if we want to take a look at a molecule with a high dipole moment like water, we see that in fact it's only about 1.82 debye's. Okay, and where does this dipole moment come from? Well, it comes from the fact that the hydrogen atoms tend to have a partial charge, which is positive, whereas the oxygen has 2 sets of unpaired electrons, making it more negative. The oxygen also tends to hog the electrons a little bit more, making it also negative. So we can see that, again, looking at the properties of the water molecule, again, oxygen is much more electronegative than hydrogen, causing the electrons to spend more time around the oxygen than the hydrogen. This gives it a net partial charge, okay, where these numbers represent some fraction of the elementary charge E. And then finally, the electric dipole moment would be roughly, if we turn it into a pure dipole, positive and negative charge, separated by some D, that would give us this dipole moment. So we know that dipole moments will basically align with exterior electric fields. And here we can see a number of different compounds and their dipole moments. Carbon tetrachloride has no dipole moment because you basically have a carbon atom at the center, and on a tetrahedron, different chlorine atoms, although the chlorine is more electronegative than the carbon, there's no side that has more positive or negative charge than any of the others. Ethanol, of course, is an alcohol, so it has an OH group, making it polar. Benzene, of course, is a very symmetrical ring of carbon. And if we knock off some of the hydrogen, replace them with chlorine or fluorine, you can actually make the benzene ring get a dipole. And again, here's water, just for comparison to a lot of these different substances there. The symmetry of a molecule really does affect its dipole moment. Again, if we think about the water molecule, we know that it has this bend between the hydrogen. And essentially what happens here is the hydrogen tend to be on one side of the molecule, while the unpaired electrons tend to be on the other side of the molecule. I believe this is a sp3 hybridization, if you remember that, and the two unpaired electrons would be sitting at other sides of the tetrahedron. With carbon dioxide, however, that's not a polar molecule. Again, remembering your hybridization. I hope I get this right. I believe it is, I might be wrong with this, so I'm going to leave this alone. It has a linear symmetry to it. So again, the oxygen is more electronegative than the carbon at the center. But again, because you've got a negative side here, a negative here, and a positive here, there's no net dipole moment, okay? Even though between these two atoms, there's a dipole moment, these two, the dipole moments within this molecule cancel each other out. So it's a non-polar molecule. And that's one of the reasons why water, remains a solid at a fairly high temperature. It's still a solid up to around 0 degrees Celsius, whereas carbon dioxide forms dry ice at a much, much lower temperature because there's not a strong van der Waals force between the molecules because it's not really polar. Again, just a slight change to molecule can really affect its polarity and its dipole moment. Here we have methane, which is completely symmetrical. There's no net dipole moment among the hydrogen. If I replace that suddenly with a chlorine, and I have a chloromethane, I can see that it's very polar. Okay, it's more polar than even water. And what's interesting is if I add 2 chlorine, it actually reduces the net dipole moment because the 2 negatives are now competing against one another. Adding 3 reduces the dipole moment further, and having all 4 hydrogen replaced brings me back to 0. So again, that's a real nice study in how symmetry affects the dipole moment. Again, polar molecules, molecules with strong dipole moments tend to have greater intermolecular forces, van der Waals forces, and therefore will form solids at higher temperatures and liquids at higher temperatures. Just a comparison, we tend to see that heavier molecules tend to have higher melting points and higher boiling points. Well, look at these molecules here. We have propane, which is completely non-polar, and has a dipole moment of 0.1, whereas boiling point is very, very low. At normal atmospheric pressure, its boiling point's 231 degrees Kelvin. So when you get a propane tank, it has to be kept under pressure, or the propane will go from a liquid to a gas. And that's why it makes such a nice source of fuel for like a propane grill. You can fill up your tank with this pressurized liquid, you reduce the pressure, the liquid begins to boil, and it is a vapor well below the freezing point of water. As we increase the dipole moment, dimethyl ether has a higher boiling point, even though it has about the same molecular mass. Chloromethane, as we saw, has a very large dipole moment, so its boiling point is also slightly higher. And here's acetaldehyde, okay? Same as propane, with its high, its large dipole moment is going to make its boiling point very high. And going to the extreme, you can see that this remains liquid at even well above, well, I guess our boiling point of water is 373. So it has a very similar boiling point to water. But again, the general trend is as the dipole moment increases, so does the boiling point tend to increase. Of course, the other important aspect of dipoles is that polar molecules can dissolve ionic compounds and basically dissolve them into solution. So anything that's polar, you can dissolve negative and positive ions. And of course, we know this is a property of water, where we can dissolve salt in it, and it can conduct electricity due to the ions that can move around.